We're now going to consider a very special graph. This is an acceleration time graph in which the acceleration is constant and has the value a, whatever that is. That could be 10 meters per second squared, a could be 5 meters per second squared, but the key thing is it's constant, so you see that it has a straight line as time changes. So this could be 1 second, 2 seconds, 3 seconds, 4 seconds, 5, 6. Let's assume that we're going to look for the change in the velocity using this graph for some given time t, of course starting from t equals 0 seconds. Well, the way to do that, of course, is to find the area under the curve. That's true for all graphs. But in this case, we have a very specific graph with a very specific shape. So what I'm going to do is I'm going to come down here to t, and I'm going to pull our little line up here and touch it on our, and what we see is that we have a rectangle. And we know how to calculate the area for rectangles. So the change in velocity, which is equal to the area of the curve, but this is a rectangle. The rectangle has a base whose length is t and whose height goes up to a. So the change in velocity for this particular shape is at. Now, we also know that delta v is equal to the final velocity minus whatever the initial velocity was. Now, if these are in the x, you would have subscripts indicating x. If you're talking about along the y, you'd have subscripts along the y. I'm leaving that out right now. This is just the final velocity and the velocity at t equals 0. Well, I can rearrange that equation to find v. So let's do that. V is equal to v naught plus delta v. That's always the true formula. But now I have a solution for delta v. For this type of graph, it's this. So v is equal to v naught plus at. This equation can be quite useful in solving problems, but it isn't true in general. It's only true when this is true, and this is only true, this equation right here is only true if this graph has a rectangle. So it only works for constant acceleration problems. This equation is known as the first kinematic equation. And is only true for constant acceleration problems. So the graph always works. This equation comes from the graph, but only for this very specific graph. So this is nice in the sense that we can plug things in and work algebra, but we have to make sure that it's true, and it's not true always. The area under acceleration time graph is always the change of velocity, but this statement that change is at is only true for this rectangle. Alright, now if we look at this, we see that we could plot now velocity versus time, and then get a velocity time graph and look at that. And that's our next step. Alright, now we go to the velocity time graph. I remind you that we got this graph, this very specific straight line looking graph, by solving a constant acceleration problem. So this is what the velocity time graph looks like if you have constant acceleration. And we had that from the formula at plus v naught. So v naught is the y-intercept. I might remind you that you see in math equations like this. This is of the same form for a straight line. There's the y-intercept right down here. The slope for this graph is the acceleration. and it's constant. That's why you get a straight line, constant acceleration. And now we want to find the displacement using this graph. Now to find the displacement delta x, I remind you that what we need to do is we need to find the area under this curve, the velocity time curve. And we can get a specific formula because, well, it's the area under the curve in general. For this graph, we know exactly what the graph shape is, so we can find the answer to it and write down a formula for it, which will be the second kinematic equation. So let's go to some time t. Let's say it's this time right here. And we'll draw a line up. And it hits right there. And at that time, if you were to drag right across, then what you would have would be the final velocity v. So that would be its velocity at time t. This was its velocity initially. Now we can see that there are two graphs, two shapes, I should say, underneath this. One is right here. Let me turn my ruler back on. So there's this graph shape, which is a rectangle, and then there is, for the area in the curve, this triangle. Now, a couple of things to note. This thing right here, let me undo that again. This thing right here, from here to right there, that's delta v, the change in velocity. Because this is v naught, and this right up here is v. And so v minus v naught is delta v. This area here, well, that's t, the change in time. On the other hand, this rectangle, we have everything we need to find it. We have a base of t, and we have this height. That's v naught. So we can write what the change in position, the displacement, is for this. So let's do that. Delta x, well, it's equal to this rectangle, which is v naught t, plus this triangle, which is 1/2 1/2, my fault there, delta v times t. So I'm going to write that over here so we just have it where it's a little easier to see. V naught t plus 1/2 delta v times t. This is the area of the rectangle. This is the area of the triangle. Now, this gives you the change in position, which is x minus x naught. So one could find the final position x at some time. It's x naught plus v naught t plus 1/2 delta v times t. And this is a totally good equation. It's not usually the way it's written in any books or anything, but it's true. It says the final position is equal to whatever your initial position was, plus the area under the rectangle. That's this. So if there is no initial velocity, if there is no rectangle, if this drops down to here, and you just have a triangle, this term would go away. On the other hand, if you had no acceleration, that is, if you didn't have a slope, if you had a straight line on a velocity time graph, then you'd have no change in velocity, and you would have no area under your acceleration time curve. And then this part would go away. That's one where an object is moving at constant speed. Now, what's usually done is they say, hold on here. Remember something. We already required the fact that delta v was at previously from the acceleration time graph. So I can take that at and plug it in here. Then I would have acceleration times time again. Well, if I do that, I get this equation. One half a t squared. This is known as the second kinematic equation. Running out of room here. Hopefully you can write smaller than I can on the screen. So the final position is equal to the initial position plus the initial velocity times time plus 1/2 at squared. Well, that equation can also be graphed now on a position time graph. And what do we have? Well, according to this, we have a parabola. The parabola whose coefficient here is 1/2 times acceleration, whose term with respect to t is the initial velocity, and whose constant term is the initial position of the object at t equals 0. So again, this equation is only true if that equation is true, and that equation true is only true for an acceleration that's constant. So this graph for velocity time graph is directly related to the constant acceleration graph. All right. If you have some graph that looks different than this graph, then this equation, the kinematic equation, is not valid. But you can still use the area under the curve. The graphical analysis is always true. This curve gives this specific equation, which is only true for that curve. All right, that covers this.